We are here to talk about Cross Data Center Replication in Apache Solr. I'm Anvi Jain, working as a software engineer at Progress Software. Progress Software is based out of Bedford, and we have offices all around the world. We develop tools and platforms that enables businesses to deliver new technologies that are adaptive and cognitive. And we provide solutions for enterprise integration, data interoperability, and application development. I would like to invite Amrit to introduce himself.
Hi, I'm Amrit Sarkar, working as a senior search engineer at LucidWorks. So LucidWorks is a search enterprise company based out of San Francisco and have offices all over the world. We have a product, LucidWorks Fusion, built on top of Apache Solr, which drives search applications. And we also provide consulting and support organizations who are using Apache Solr as their search or analytics technology.
Yeah. So moving forward, the agenda for today's talk will begin with an introduction to Solr. Then we will talk about the motivation behind building this feature, that is CDCR. And then we'll give you an insight about CDCR, the components present in it, the approaches that we've used, and we'll end with a short demonstration. So Apache Solr, as you all know, is an open source search engine that is built on top of the Lucene library. It is highly scalable, reliable, fault tolerant, and has various features like auto-completion, highlighting, deduplication, learning to rank, among others. Solr is used as a search engine and navigation in the top websites of the world. The Solr Cloud mode basically powers the distributed searching, and it has the following major components. The Zookeeper that acts as the manager for the whole Solr Cloud and stores its configurations and the cluster state information, that is which node is alive, which is node, and which is not, and on which node the leader resides, etc. The collection, as you can see here, is a logical index in a Solr Cloud. And a collection can be further divided into logical chunks of data, logical slices. Every logical chunk is called as a shard, and every shard may have multiple copies, which are called as replicas. So out of these replicas, for every shard, a leader is elected by the Zookeeper, and the Zookeeper holds information about other configuration informations about the leader. So what was the motivation behind building this feature? So as you all know, no data center is completely disaster-proof these days. A disaster can be man-made or natural, or can be due to any malicious activities, leading to a loss of huge amount of data, due to which companies can incur huge financial losses as well. If you'll see at the graph over here, the cost of 1 day of downtime for an organization can be huge. And every company may not have the means to set up a proper disaster recovery strategy in place. And even if they do so, the strategy should be reliable, should be revisited regularly, and should be maintained from time to time. There are a couple of disaster recovery strategies in place, and some of them can be incorporated in Solr as well. What we can do is, we can index data into multiple data centers simultaneously. For that purpose, we can use a messaging service like Apache Kafka. Now, so what we can do is, we could redirect our data to Apache Kafka, and Kafka will handle the redirection to multiple data centers simultaneously. The overheads in this approach is, you need to configure Kafka at your own level. You need to know the proper configurations. Plus, the data at all the data centers may not be consistent, because due to any failure at any one of the data centers, you might have an inconsistency of data. And if there is such a behavior or such an instance that happens, we'll have to re-index data to that particular data center to maintain consistency everywhere. Another approach that can be used is disk mirroring, that is copying the entire hard disk from one location to another, or secondary storage from one location to another. Now, as you all know, the data in today's world is huge, right? Gigabytes to petabytes. And disk mirroring may take a significant amount of time to copy the data. Also, while copying, what if the data gets corrupted in between due to any error state or so? The whole copy that we have maintained will become useless, will be of no use. Then another thing that can be done is taking regular backups. So this approach basically involves taking backups incrementally. Also, this approach is more useful when the amount of data is less. And the backups should be maintained outside the server, because there's no point in maintaining the secondary backup in the same server where data can be lost due to any disaster or any error state. So the data should be maintained outside the server, and it should be retrieved quickly whenever needed. And here also, if the backup is incomplete due to any errors, the whole data will be useless. Then there is an internal API present in Solr itself, which is the backup API, and it is available at the collection level. This API takes backup of the entire collection and its configurations. And this API is also, again, prone to failure at live indexing or due to any error states, say out-of-memory exceptions or power failures or anything. So as you've seen, there are a lot of strategies we have in place right now as well. But all of them are not very reliable, not robust, and they require a lot of human intervention as well from time to time. To avoid all these things and to remove all these shortcomings, CDCR, or Cross Data Center Replication, was introduced in Apache Solr, and I would like to invite Amrit to give you an insight about it.
Thank you. So in the next few slides, we will see how Cross Data Center Replication actually works and how it is better than the other stated strategies. So this particular feature was added around about 18 months ago in version 6.0. If I have to define this feature in one single definition, it would be forwarding updates or actions to secondary cluster or clusters, monitor their application, and make sure that all the clusters involved in the CDCR operations are up and healthy. It supports both unidirectional, that is transferring data from one data center to other data center, and also bidirectional, that is all the data centers will be in sync automatically. This particular feature is implemented at the collection level, and only data is configured, configurations are not. So when data is replicated, configurations are not. It is a responsibility of the designer and the developer to make sure that all the entire topology and all the configurations in the respective data centers are consistent. We have multiple APIs available to start, stop, and get the status of the CDCR process, like action start, stop, and status. Now, this is how a unidirectional approach looks like. We have the source data center and the target data center. Now we will, as we have mentioned, that the CDCR is implemented at the collection level, so we will just call it source collection and target collection. Each collection have 2 shards and 2 replicas. If you look closely, the data is getting transferred from the leader nodes at the source to the leader nodes at the target. That is, only the leader nodes are allowed to talk to each other, communicate each other. This particular strategy is active-passive approach. That is, you can do the live indexing in one of the primary collections, and all the respective other collections will be kind of like a hot standby. This is how a sample configuration of the unidirectional approach looks like. We will discuss all these configurations in bit detail in the later slides. What we really like you to focus is up on the ZK host string and the target parameter value. So at your source, you can define your target's zookeeper connect string, and you will define the target collection value. You can have multiple sets of these kinds of configurations for your X number of targets at your source. So now let's discuss the underlying concept of the CDCR, of what exactly it do. So as I mentioned, updates are forwarded from the leader nodes at the source to the leader nodes at the target. Each update operation in a Solr cloud is embedded with a unique version. That particular version is based on time. It looks like something like 16017 and something like that. And this particular unique version is maintained as a checkpoint, as a persistent or a permanent node at the target, and a temporary or an ephemeral node at the source. These particular checkpoints maintained at both the centers should be synchronized at all the points to make sure that there is no loss of data. Also, this particular strategy does not require any additional network traffic. And the natural update workflow of the Solr cloud, that is, if an update operation has been received by a collection, it will be first be sent to the leader node of the particular collection. The leader node has the responsibility to forward these particular updates to its own followers. This particular strategy makes sure that all the data gets replicated to all the nodes at both source and target. So these are the core components of the CDCR of it is built upon. So first, for the first type synchronization, that is all the data should be replicated from the source to target for the first time, buffer and bootstrap gets into action. While after the initial sync is in place and you want the smooth forwarding of updates, Replicator and update log synchronizer make sure that happens. Starting with initial sync, so let us suppose the target is not available because it's not being created or being down for a significant amount of time. And a huge chunk of data has been already being indexed at your source. There are a number of documents already there. You would like to transfer the data from source to target in the best possible manner, in timely fashion, and with minimal resources. Buffer and bootstrap make sure that it happens. Starting with buffer, we would like you to focus on the left-hand side and the CDCR request handler. That's a Java class available in the Solr source code, which is responsible to process all the CDCR-specific APIs. This particular configuration is put into the Solr config.xml in a Solr collection, and it is mapped to the endpoint CDCR. Now, buffer in this example is enabled. So whenever buffer is enabled, all the references to the updates has been sent to the source will be kept in memory indefinitely until they are transferred to the target. This particular strategy works very well when the number of updates are limited, are in check. But if it gets unbounded, you will bound to face issues with threads or with heap memory. So it is best to disable the buffering during normal operation or when the normal replication is in place. APIs are available with action equal to disable buffer to disable it, and action equal to enable buffer to enable the buffer. Next, we have Bootstrap. To mitigate this limitation of not being able to handle huge amount of updates, Bootstrap was introduced in 6.2. So at the first time when target gets up, the target collection is up, its checkpoint is negative, it's -1. So when source sees that the target checkpoint is -1, it will trigger a bootstrap operation. Bootstrap essentially is copying data from one place to another. In this particular case, the data is replicated from the leader node of the source to the data directory of the leader node at the target. Once this copy finishes at the target, all the non-leader nodes will issue a collection API called request recovery. It says that copy the index from my own leader. So it's absolutely simple. It's A to B and then C that all the non-leaders at the target pull from their own leader. This particular bootstrap operation is also available through an implicit API, which can be fired on the target like this. It's not really mentioned in the documentation and nowhere in the any blog post and anything. The reason being, this particular bootstrap leverages the Apache Lucine's index fetch operation, which is a single-threaded process. And if the index is too much big or it's too huge, this particular operation can take a significant amount of time. So you want to make sure that you can leave this particular operation to the Solr itself of when to trigger and when to not, and not do something like this manually. Next, we have some supporting components too, which make sure that everything and all the components are in sync with each other. So we have state managers, which keeps a tab on certain zookeeper nodes, and whenever some changes happens, they will trigger some action. So process state manager keeps a tab on CDCR state. On the left top corner, you can see process started, buffer disabled. If an API is issued to stop the process or enable the buffer, it will inform all the respective components that some kind of change has happened. Similarly with leader state manager, which keeps a watch on top of state.json, which looks something like this. So we have a collection city bike. It will contain the information of how many shards are there, which particular nodes contains which particular replica, which replica is a leader, etc. So whenever a leader changes at the source level or at the target level, the leader state manager will inform all the respective core components that some kind of change has happened. So we have discussed how the initial sync should be done, or initial sync is done. So once the source and the target are at least in sync for the first time, now new updates are being sent to the source, and they need to be propagated to the target in a timely fashion. A replicator makes sure that happens, and it forwards the updates in batches and at regular intervals. These batch size and the interval are specified in Solr configured XML. So let's suppose you have very heavy indexing going out at the source, or you have very heavy query load. You would really not like the other components in Solr to overwhelm that particular process. You would like the performance to not be affected by something CDCR, which is used to have a hot standby. So this particular strategy, that is sending the updates in small batches and in interval, makes sure that performance is not affected. So in this particular example, we have a batch size 128 and have a schedule of 1,000 milliseconds, that is 1 second. Now let us suppose 1,000 updates have been sent across to the source, which needs to propagate it to the target. It will take around about 7 to 8 seconds to reach to the target. There will be a slight delay, but that is something we have to cope up with. After each successful operation, checkpoint is updated at the target and propagated back to the source so that they can be synchronized. And if a leader goes down, the newly elected leader will come up and will start the replication from itself. And if a target is not available or being down for a significant amount of time, replicator will try to forward the same batch again and again indefinitely until the connection is restored. Now, at this particular point of juncture, what you really need to do is stop the CDCR process and do a basic diagnosis at your respective targets. Next, we have the update log synchronizer. So, as I said that all the leader nodes are only allowed to communicate with each other, but what happens when a leader node at the source goes down? Now, I understand that we are using leader, non-leader terms a lot in these particular slides, but it's important to understand it. So what happens when a newly elected leader comes up after one goes down? From what point it has to start the replication? That's being maintained by update log synchronizer. So each non-leader at the source only will ask its leader that what is the checkpoint at the corresponding target in regular intervals. In this particular example, we have that interval set as 60k milliseconds, that is 60 seconds, 1 minute. So whenever the newly elected leader comes up, it will start the replication from the last checkpoint it already has. It may replace some updates, but it will make sure that no updates are lost in the process. The last component we have is CDCR update processor factory. So as I mentioned in the underlying concept, Solr has a tendency to add a version to every update operation, no matter where it is coming from. So when an update is forwarded from source to target, it already has a version. And you would really like to use the same versions to have the synchronization. But Solr tends to override it. CDCR processor factory makes sure that it does not override that. This is how you can define the CDCR update processor factory. You would define it at update request processor chain, which will be a default chain of the update endpoint. If you really like to understand what is request handlers, what is update request processor chain, or update processor factory, check out the official documentation to understand them better. So we are done with discussing the components of CDCR, and now let's discuss the monitoring APIs we have. So we have 3 APIs available as of now. The first is queues, which provides us information of how many update a target is behind the source, and what was the last timestamp a successful operation was executed at the target. Right? It will contain some more intrinsic information regarding the transaction log sizes and numbers at the source. We really did not discuss about the role of transaction log in this particular talk, and we have it abstract. Check out the documentation or the reference links at the end of the slides to understand them better. It also contains information about update log synchronizer, whether it is running right now or being stopped. Then we have the operations API, which provides information about the average number of operations being executed at a particular target per second. And those are broken down into average number of deletes and average number of adds. We have the last one, errors API, which will provide information about the consecutive errors and the cumulative errors occurring at a particular target. It will also provide information about if there are any bad requests or internal errors happening at a target, so that you can stop the CDCR process and do a basic diagnosis on that respective target cluster. Now I will invite back Anvi, who will take us through the bi-directional approach and the rest of the slides.
Yeah, so far we have discussed about the unidirectional approach, which was an active-passive approach, where the indexing can be done only at the source, and for the targets can be used only for the querying purposes. So to remove this limitation, the bi-directional approach was introduced in version 7.2 of Solr, which is a passive-passive approach, and there is no concept of a source and a target. So if you will look at the pictorial representation over here, we could see that all the data that was indexed into cluster 1 is being shared with cluster 2, and all the data that is indexed at cluster 2 is being shared with cluster 1. So this is done simultaneously, and there are no source and target. Every cluster has its own, every cluster is just the same over here. And since that is why it is an active-active approach. So if you will look at the configurations, in the cluster 1 collection configuration, the zookeeper is pointing to cluster 2, and in the cluster 2 configuration, the zookeeper is pointing to cluster 1. Also, the target attribute for cluster 1 is pointing to cluster 2, and the target attribute for cluster 2 is pointing to cluster 1 similarly. So this is how basically the CDCR, the unidirectional approach was enhanced or updated into the bidirectional approach. If you will look at the unidirectional approach, whenever an update comes to the source, it indexes the data into itself and just pushes or forwards the data to the target, and the target indexes into itself. In case of a bidirectional approach, with the update, a new flag was added, is CDCR. If the value of the flag is CDCR is set as false, that means it is a normal update, and if the value is set as true, that means it is a CDCR update, or it has come through another cluster. So whenever an updates come to cluster, say cluster 1 here, the flag is set as false. What cluster 1 does is, it indexes the data into itself, sees it's a normal update, that is CDCR is false, marks the flag as true, and forwards the update further. Now that update now, say suppose comes to cluster 2. Cluster 2 sees that the flag is CDCR is marked as true. It just indexes the data into itself and does nothing. So the bidirectional approach makes it possible to have a cluster of Solr clusters. If you will see here, every cluster is in constant conversation with each other, and there is no concept of a source and a target, and there is no center of this entire cluster. Thus making it possible to have a decentralized multi-cluster setup. So the gist of the whole bidirectional approach is that there is no source, no target. It's a decentralized cluster. There is no single point of failure anymore. And since in the bidirectional approach, indexing can be done to any of the clusters, hence in case of a failure, the indexing can be moved from a failed cluster to a working cluster with minimal human intervention. And this adds an advantage of dividing the whole traffic geographically. So say for example, I have one data center in New York and another data center placed here in Berlin. What I can do is, I can divert whole of my US-based traffic to the New York placed data center, and whole of my Europe's or eastern part of the world's based traffic to the Berlin data center. This would reduce network delay and provide much better search experience. So we will be giving a short demonstration on the approaches, the unidirectional approach, the bidirectional approach of CDCR. For that purpose, we have created an application, an analytics application on Apache Zeppelin. Yeah, so the data we have used is of bikers, the distance traveled by them from one place to another, the time taken by them, their gender, classifications and all. And we have created some graphs and configuration graphs around it. Our Zeppelin application is currently pointing to cluster 1. And the cluster 1, the configurations for cluster 1 solar, if you can see, the zookeeper is pointing to cluster 2 for cluster 1. And for the cluster 2 solar, the zookeeper is pointing to cluster 1. The name of the the name of the collection is same. We have kept them same for both the clusters, which is city bike over here. We will reload solar cluster 1, and we could see that there are no documents over here. And we'll reload solar for cluster 2, and again, there are no documents over here. And similarly, if you reload the CDCR for both cluster 1 and cluster 2, we could see that it's stopped right now. So what we will do is, we will index some data into cluster 1. And since our Zeppelin application is pointing to cluster 1, we should be able to see the graphs we've plotted around the application, around the data, sorry. So we could see that there are around 80,000 records now present in cluster 1, and we could see all the graphs and all have come up. And if we'll reload solar, for cluster 1 there are 80,000 records. Similarly for cluster 2 there will be 0 records since CDCR is not started and it's just a single cluster as of now. Now we'll start CDCR on cluster 1 and we'll disable buffer. So what this should do, this is kind of a unidirectional approach where we are using cluster 1 just for the indexing purpose, and cluster 2 can be used for the querying purpose as well. So in this is cluster 1, right? Yeah, cluster 2. In cluster 2 also now we can see 80,000 records because CDCR was enabled. All the records that were pushed to cluster 1 has been shared with cluster 2. And with CDCR enabled on cluster 1, we'll again index some data onto cluster 1. And the same should be copied to cluster 2 as well. So if we'll run the application, we could see around 160,000 records are present over here. And if we'll reload cluster 2 for solar, we could see around 160,000 records here again. Now we will enable CDCR on cluster 2. Now this will become a bi-directional approach since CDCR is enabled on both the clusters. Now we can index data as well onto the cluster 2. And both clusters now can be used for indexing and querying purpose. Yeah, done? Yeah. Now say for example, our cluster 1 goes down due to any reason. Some failure, out-of-memory exceptions or anything. So for that purpose, we'll kill cluster 1 right now to demonstrate that. And we'll reload the application. We've written down these shell scripts and we've shared them on the GitHub handle that we've mentioned on the references page. You can go and have a look at them. This might take some time. Yes. So since our application is failing. Now since we have a backup at cluster 2, what we can do is very smoothly, we can just point our application to cluster 2. And within no time, we can see that the data is back again, our application is up and running again. Yeah, it's taking some time. Done? Yeah, so if we reload the application,
all right, we're back.
Our data is up. We are again able to see the 160,000 records. Now, since our cluster 2 can be used for indexing as well, what we will do is we will index some data. Yeah, so cluster 1 is down now.
Yeah.
Right now. We'll index some data onto cluster 2 now. And if we'll reload the Solr cluster, we could see around 220,000 records over here. And the Zeppelin application should also have the same number of records. Now say we found out the reason why a cluster 1 went down and we'll restart the cluster. Now what this should do is, since CDCR is enabled on both the clusters, whatever data that was indexed into cluster 2 after cluster 1 went down should be transferred back to cluster 1. That's how smoothly it works. So we're just starting the Solr cluster. Yes. And if we'll reload Solr, cluster 1, it might take some time. Yeah. So we have the same number of records that we indexed to cluster 2 in cluster 1. So that was all about the demonstration for CDCR, the unidirectional, bidirectional approach, and how smoothly things work. I mean, with minimal intervention, you can just point your applications to any available clusters that's present. So we've discussed a lot about CDCR, but like any other feature, it has some limitations too. The first thing is, the CDCR specific properties must be specified in solrconfig.xml at the time of the collection creation itself. If you want to enable CDCR on an already created collection or on a non-CDCR collection, that is not possible as of now. Another thing is that whenever a CDCR specific property is changed in solrconfig, the whole collection requires a reload right now. And since, as already mentioned, Bootstrap is a single-threaded process. And if the amount of data is huge, which needs to be copied from one cluster to another, Bootstrap may take a significant amount of time. And CDCR does not support transaction and pull type replicas as of now. Solr has 3 types of replicas: NRT, near real time, transaction, and pull type, out of which only NRT replicas are supported. So there will be some improvements that will be coming around CDCR and Solr. The first thing will be moving the configurations from solrconfig.xml to Zookeeper. What this will do is, it will remove the limitation of reloading the entire collection whenever a CDCR specific property is changed. Then some new APIs will be added. The reload CDCR, modify CDCR, and support for transaction and pull type replicas will be added in the future. Sorry, yeah. So this is the references page. You can go and have a look at them. They'll give you more knowledge about the CDCR feature and give an insight about things. We have also mentioned the GitHub handle where you can find the scripts we ran while the demonstration. That's it from our end. Thank you very much. We would like to welcome any questions you people have.
Yeah, we finished a bit early. But
Yeah.
Right. Right.
So in case of this bi-directional synchronization,
Right.
what happens if there are 2 conflicting updates?
There are 2 conflicting updates.
The conflicting updates. Yeah, that's a great question actually.
No blockchain, please.
Yeah, yeah. So if a same update has been sent to both the centers at the same time with the same timestamp, they will be indexed into itself, forwarded to each other, and one of them will be rejected at the other end. So what really happens is, the version of the update should be greater than the current one to be indexed to itself, to get accepted. If the index is not bigger than the already one there, it will be rejected anyway. So when you are doing the simultaneous indexing to both the data centers, you have to make sure that you don't set the same update at the same time. Otherwise, obviously, let us suppose a data center at the Berlin has indexed the same update, and at someone in the New York has updated the same update. One of them will not be able to see his own update, because that will be overridden by either one of them. So
they will be synchronized, but one of the updates will be lost.
Yeah, that will be more like not lost. It's more like depending on the version it has been assigned on the basis of the machine's timeline, right? Because these versions are calculating to the server's machines. So if these machines are in sync, let us suppose they are in CST timings or maybe in EST timings or something like that, then we will ensure that at least one of the updates will be there all the time of whatever has been received after. But yeah, I'm like, this is one thing we, even in the documentation, Solr official documentation, it is absolutely mentioned that always index at one data center at one time, even if you have the bidirectional in place. Yeah.
Okay, thanks.
All right, thank you.
All right, thank you. All right.
Yeah, thank you very much.
Thank you.
All right, thank you.
Thank you.
Thank you so much.